All right, in this video, we're going to look at error in approximating a integral with both the trapezoid and Simpsons rule. There are formulas for both. So if you look at the problem, we're going to evaluate this using trapezoid and Simpsons, and then calculate the actual maximum error we could have made. So um, you I'm assuming you know how to do watching this video. You've already been through trapezoid and Simpsons rule. If you need to look at other videos about that, look at that. But uh, best thing to do would be pause this video and actually calculate this yourselves, and then check your answers. So here's my answers. And then I went ahead and figured out, well, what was the actual error in my calculations? So you can easily figure out that this integral is actually equal to 2/3. So I just took 2/3 and subtracted what I got with the trapezoid and Simpsons to get these errors. So obviously the Simpsons is a much better approximation. And that error was 0.0048 as compared to the trapezoid, which was 0.038. So those are all the calculations. Now let's calculate what the maximum error could be. So we have formulas for that. Here's the one for the trapezoid rule. They look pretty complicated, but they're pretty easy usually. There's a trapezoid rule. The big thing is this max absolute value of the second derivative of x. This video will explain that. Everything else is pretty straightforward. And here's the error for Simpson's rule. Pretty similar, but the max is the fourth derivative. And we'll explain that in a second. So let's start with the error in the trapezoid rule. We're going to have to get the second derivative. So it's part of the formula, so let's do it. Our function was 1 over x minus 1 squared. So x minus 1 to the negative second. This will be easy to take the derivative now. So the first derivative is a simple chain rule. It will be -2 times x minus 1 to the negative third times the derivative of the inside, which is just 1, so that's really good. The second derivative is just the same type of simple chain rule, which is 6 times x minus 1 to the negative 4. I'm going to simplify that because that's the one I'm going to be using. I'm going to go on here because if you saw the Simpsons rule went down to the fourth derivative, so I might as well just do that now. 6 times negative 4. And then the fourth derivative, -5 times 124 is 120. Okay, so we're on the trapezoid rule. The error has to be less than this quantity. B minus A is easy. Those are our limits, A and B. N is the number of intervals we use, which was 4. That's easy. We just have to figure out what the maximum of this derivative, of the absolute value of this derivative is. Now that may seem a little complicated, but it actually is pretty simple. And by the way, I should say this, it's the maximum over the interval, R interval 2 to 4. So it's pretty easy when you have a fraction. So here's how you're not quite sure how you're going to do this. Let's just look at two fractions with a constant denominator of 6, or numerator of 6. And it doesn't have to be 6, ours is. Say you had 6 over 10 versus 6 over 100. Well, it's very obvious that 6 over 100 is less than 6 over 10. So 6 over 10 thus is bigger. So you can, a generalization is if you have the same constant numerator, as the denominator gets bigger, the fraction gets smaller. So in this case, we want the biggest this derivative could be on the interval from 2 to 4. Thus, we want the denominator to be as small as it can get, thus making the biggest fraction. So from 2 to 4, 2 minus 1 would be 1 to the 4th, as opposed to 4, which would be 4 minus 1, which would be 3 to the 4th. 4 would make the denominator much, much bigger. We want the denominator to be small because that would get us the maximum, just like this. Therefore, I'm going to plug in 2 for x, and that would give me the maximum value of this. So the maximum value of that derivative from the interval from 2 to 4 would be exactly this, which is a nice number. It's 6 over 1. So now we're good. So the error is going to be very easy to calculate. The error of our approximation, and plus or minus, so we're going to use absolute value, has to be less than b minus a cubed over 12. We used 4 intervals, so times 4 squared, times the maximum value that derivative can be, which we just calculated to be 6. So the error has to be less than 2 cubed divided by 12 times 16 times 6. So we're guaranteed that our error, this is 0.25, that our error is going to be less than 0.25. And just our error is 0.038, so much, much closer than the 0.25 that we would have calculated. But it could never be over 0.25 in this situation. So that's it. Now, Simpsons rule, we're done, basically. So all this is plugging in, because for the Simpsons rule, we already said the fourth derivative was 120 over x minus 1 to the 6th. So this is the maximum of the absolute value of 120 over x minus 1 to the 6th from 2 to 4. So this is going to work out the same way. We're looking for the biggest denominator the smallest denominator that would give us the maximum value of the fraction. And going from 2 to 4, that's going to be 2, because anything bigger than 2 would make the denominator bigger. So our maximum would be 120 well, we don't have to put max because I know this is a max, over 1 to the 6th. So now again, that's it. Now we just plug in, and I'll do this a little bit quicker. B minus A is still equal to 2. 2 to the 5th is 32. This will require a calculator here. 180 times, we're using 4 intervals, so it's 4 to the 4th. I think it's 256, but I don't trust myself. And then times 120. So 32 divided by 180 times 4 to the 4th, and then times 120. And I have the maximum error with Simpsons is 0.083 repeating. That's 1/12. And if you look at the actual error we got, that was 0.0048. So we did much better than the maximum error would have given us, but that's it. So the that's interesting. But then there's other problems that will ask, all right, so you have this function. How many intervals would you have to use so that your maximum error will not exceed a certain number? That's where this is more useful, and that will be described in the next video. So that's all for this.